Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we discussed the adiabatic process. Today, we will be learning about the microscopic view of matter, that is, the examination of matter on a level not visible to the naked eye. Are you ready, everyone? Let us begin. To understand matter on a microscopic level, we must first learn about the kinetic theory of gases. This theory was derived from a series of experiments, beginning in 1827 with the theory of Brownian motion, introduced by Robert Brown. Robert Brown examined the behavior of pollen grains suspended in water and observed the movement of particles as they moved around within the fluid. His studies showed that particles in liquid and gases move in random directions at very high speeds. Therefore, Brownian motion is defined as the apparently random movement of particles in fluids caused by the impacts of molecules of the fluid. This discovery was an especially important one in Einstein's studies, which used Brownian motion to provide some credibility to the existence of atoms. The seemingly erratic movement of particles can be easily observed through a microscope. In doing so, we can examine the kinetic behavior of particles in a methodical way. From Brownian motion, a theory on the kinetic properties of gases was founded. Consider a single particle of mass in a box-shaped system as you see pictured here. The particle of mass, m, is traveling at velocity v towards the side of the box. The particle will collide with the shaded wall and rebound with a velocity of minus v. The change in the particle's momentum is 2mv. The particle bounces backwards and forwards within the box, exerting force on the shaded wall, but only for a very short duration. Since the box has a length of x, the time between two successive collisions on the same side is equal to 2x over v. Newton's second law states that force is equal to the change of momentum divided by the time taken. So in each time interval of 2x over v, the wall will cause a change in momentum of 2 times mass multiplied by velocity. From this, we can conclude that the average force on the particle by the wall is mass times velocity squared divided by the length of the box. Newton's third law explains that as the wall has exerted force on the particle has exerted an equal and opposite force on the wall, resulting in the average pressure. The average force exerted on the wall over a series of collisions, therefore, equals mass times velocity squared over XYZ volume or the dimensions of the system. As pressure is equal to force divided by area, and the area of the shaded wall is YZ. The average pressure on the shaded wall due to the motion of a single particle is mass times velocity squared divided by volume. Since there are really several particles in the system, we can apply the variable n to the number of particles present in the box moving in random directions. On average, 1/3 of the particles will be colliding with the shaded wall and the opposite wall. Another 1/3 will be colliding with the other 2 sets of walls in the system. The total average pressure on the shaded wall is therefore the number of particles times mass times velocity squared divided by 3 times the volume. The total mass of the gas is Nm. So we can replace the value of Nm over 3 with the density of gas, represented by rho. Thus, the total average pressure is density rho times velocity squared over 3. Since there will be a very large number of particles in almost any system, we must establish the range of speeds for each particle. Since it is the mean pressure that we can measure for any gas, our expression can only provide us with the information on the mean of all the square speeds of the particles. This is called the mean square speed. Finally, the pressure of an ideal gas can be written in terms of microscopic quantities. Thus, pressure is equal to 1/3 the density of the gas times the mean square speed of the particles. Students, let us do an activity. What is Brownian motion? Who developed the theory? Why was this discovery important? You may begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Let us answer the question together. Brownian motion is defined as the apparently random movement of particles in fluids caused by the impacts of molecules of the fluid. The theory was developed by Scottish botanist Robert Brown in 1827. The discovery was of critical importance because it helped to justify the current atomic theory and also provided us with the basis for the kinetic theory of gases. Great work, everyone. In Brownian motion, the average distance covered by a particle between impacts is called the mean free path. This is often represented by the symbol lambda. In a gas, the lower the pressure or temperature, the greater the mean free path of particles. The Brownian motion theory was not the only one that helped define the kinetic theory of gases. There was also the concept of diffusion. This is the process where particles in a fluid spread from a region of high concentration to a lower one. In this example, a drop of orange juice is dropped into a glass of water. Notice how the concentration slowly separates and spreads. This study helped to establish the kinetic theory of gas as it exists today. Now we have two equations for the kinetic behavior of gases. One for macroscopic study and one for microscopic study, based on the model of kinematics of particles. The two formulas are listed here. Resolving for pressure and volume in both equations gives us 1/3 the number of particles times the mass multiplied by the mean square speed equals the number of moles times the molar gas constant multiplied by absolute temperature. From the definition of a mole, we know that the number of particles will be equal to the number of moles times Avogadro's constant. So the equation is further reduced to 1/2 the mass times the mean square speed is equal to the molar constant times absolute temperature over Avogadro's constant. For the average kinetic energy of a particle, EK equals 3/2 times K multiplied by T. K, in this case, is called the Boltzmann constant, which is the gas constant for one particle of gas. The Boltzmann constant is equal to the molar gas constant divided by Avogadro's constant. The value of the Boltzmann constant is 1.38 times 10 to the power of negative 23 joules per Kelvin. Students, we have time for one more activity. Define the terms mean free path and diffusion. Provide 3 examples of diffusion.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. Here are the answers to your questions. The mean free path is the average distance covered by a particle between impacts. It is represented by the Greek symbol lambda. Diffusion is the process in which particles in a fluid spread from an area of high concentration to a lower one. An example of this could be the use of food coloring in water. Another example might be observed by spraying perfume. If you spray perfume in one area of a room, with time, you will smell it on the other side of the room. The particles travel from the high concentration at the nozzle of the bottle and become more diffuse, spreading throughout the room. This concludes today's lesson. We have learned about diffusion, Brownian motion, and the kinetic theory of gases. Until next time, thank you, teacher. Thank you, students.